Look, Snickers, somebody brought us a tube. Yes, a tube. Snickers voiced his opinion that he prefers the warm tube sound. Don't you, Snickers? Look up and say hi to people. People want to see the Snickers. I guess it's sleepy time. Hey everyone, welcome back to the John Audio Tech channel. Today is kind of a mailbag day. This came in my P.O. box. A little tube amp. It looks like a little preamp of some sort. And also included these little tubes. This looks like a China 12AU7 and 6 p.m. And where is it? There it is. A 12AU7A. And I don't know if you can see that, it says USA. So that might be new old stock. Looks to be in good shape too. It looks unused. Or at least very lightly used. Kind of interesting though. The different plate sizes here. The element sizes are different among these tubes. This is like 2/3 the size, the plate area, and the Chinese one. Surprise, surprise. Well, this will be interesting to try out, see if it works. It appears to be a kit that was put together. Did not include any sort of schematic, so first order of business here would be to kind of reverse engineer this thing into a schematic and see what I can come up with. And here is the schematic. I think I have everything right, all the values put in. Now I'm just showing one channel of the amplifier because the other channel is going to be the same. No sense in duplicating the effort. So what we have going on here, we have the signal coming in going through a 10K potentiometer. Then it goes on through this 47 or 470 nanofarad capacitor right on into the grid of the tube. 1 mega ohm biasing resistor. There is no resistors or anything in the cathode circuit, so they're hoping that the tube parameters are within a certain tolerance so it doesn't affect the circuit too much. This up here is the supply rail, and it goes to a 47K resistor, which is your plate resistor. Notice that the plate is connected directly to the input of the op amp. The part number of this op amp, 4556, tells me that this is meant to be a headphone amplifier. The reason why is your ordinary op amp, like a 5532, has an output current of around 25 milliamps, give or take. But this op amp can put out about 70 milliamps, so it has the extra current for driving headphones. It's also a buffer because the output is fed directly back into the inverting input. So this has no voltage gain. It's just going to take the signal right off the tube and send it out to the headphones. Its purpose is to increase the drive current for the headphones because a tube circuit has very high impedance. It's not going to be able to drive headphones directly. This is a single supply circuit, so the output of the op amp is going to have about half the supply voltage on it. And you don't want that DC getting out to your headphones, so they have a blocking cap there, a 470 microfarad, that will couple the op amp to the output. Next, there's this 47 ohm resistor, and the reason for that, I think, is to increase the output impedance of this circuit. Even though this op amp has higher drive capability, 32 ohms would still present a challenge, so they increase the output impedance by adding this resistor there. Also, if there's any capacitive reactance in the load, it helps to prevent the op amp from oscillating. It kind of pads that down with that resistor. Next is this 1K resistor that connects from the output to ground. The reason for that, I think, is an anti-pop circuit. Let's say you powered up the circuit without headphones connected. Now if this capacitor is discharged and you plugged in your headphones, suddenly current's going to flow through there to charge that capacitor and you'll get a loud pop in the headphones. And you don't really want that. So having that 1K resistor there will allow that capacitor to charge up, and there won't be a differential voltage when you plug in your headphones, so you won't get that pop. Another interesting thing with this circuit, being single supply, like I said, you're going to have half the supply voltage on this output. Where do they set that? You know, this is just a unity gain buffer. Well, it's the tube doing that as well. It's going to set this output voltage to somewhere around half the supply voltage, and being a buffer, it's going to pass that on through. Down here is the filament supply, and I'm a little baffled why they did what they did. They have a LM317 set up in constant current mode, because you can see here they have two 10 ohm resistors in parallel to equal 5, and on the other side of those connects back to the adjust pin. So if I take the reference voltage divided by 5, it's set for 250 milliamps constant current. So I'm not sure why they just wouldn't use 12.6 volts here. Why are they using constant current? I guess one potential reason is when you first power it up, these are cold and would draw extra current. So this would not stress the filament as much. That could be one reason. Another problem is if this is a 12.6 volt circuit, you know, this supply is actually here as well. I just separated it out for discussion. The dropout voltage of these regulators are around 2 or 2.5 volts, depending on the current. And this wouldn't properly be regulating at a 12.6 volt supply, so maybe this has to operate at more like 15 volts. I couldn't see it being much higher, because then you'll start heating up the regulator. You know, there's no heat sink on it. So yeah, it's kind of a odd circuit, I guess. And one final thing about this circuit, there's a 560 ohm resistor and a LED. I noticed that when I was looking at the traces on the board, something was going to the center of this tube socket. And I didn't see it at first, but when you look down in there, there's a little red LED. So I guess that shines light up into the tube and kind of makes it look cool or something. Yeah, whatever. Now a big fail with this circuit is no supply bypass capacitor. None at all. That's an engineering no-no. I guess they can get by with it. We'll see when we test this thing out, but yeah, there is no supply bypass on this thing at all. Well, let's hook it up and see what it does. Okay, I have it all set up here. I have the outputs connected to two 100 ohm resistors as a load, which we'll be testing momentarily. So I fired the thing up and took some measurements. Well, at 12.6 volts, the filaments were only running at 10.2 volts. And that can work if your tube is in pretty good shape. And like I was saying, you know, the way they have this set up as a constant current source, you're going to have the dropout voltage of the regulator and some voltage drop across these resistors. So the filaments are underrun in this case. Another issue is the plate voltage is a bit high, meaning the tube's underbiased. It's running out around 8 volts with 12.6 volt supply, which means underbias. I mean, it'll work, but you're losing some headroom. It's going to clip on the positive side of the signal. So I cranked it up to 14 volts. think it would work better turned up a little bit. So let me measure the filament voltage. 11.6 volts. So yeah, we're still not up to the proper voltage. Let me check the plate voltage. The plate is connected directly to the non-inverting input on the chip. 9 volts. Sorry about the glare. Not much I can do about it. Now, being a buffer, we should get the same voltage on the output. Oh, that's the supply voltage. The output's right here. Yep, exactly the same. So it's a DC coupled buffer, so the exact same voltage is going to appear on the output. So let's check the other side, the other channel. Now this is running about 7.5 volts. So that's better. That's closer to midpoint. So yeah, it's the tube parameters causing that difference between the channels. They should have used a voltage divider on the grid to set the tube probably a little on the positive side, maybe try like 0.5 volt, because running at such low voltage you'll have to coax the electrons to flow to the plate. They also should have used a cathode resistor, which would have helped to isolate the tube parameters from the circuit and allow the bias to be more stable. But again, this is a simple circuit. They didn't do that. Okay, now let's put some signals on this thing and see what it looks like. Okay, here is the signal output. Again, I have 100 ohm loads across both channels. I turned the supply voltage up to 15 volts. That puts the filament voltage at 12.6, what it should be. Even so, the tube is still under biased. And as I crank it up, you can see it clips on the positive rail. As I tune it down, pull it back to a more normal level, yeah, getting a decent voltage swing, 1.2 volts, which should be good for driving the headphones. Let's take a look at the distortion now. Turn this off. Like always, we have the pilot signal here, 1%, and the fundamental, but look at this. We have a big second harmonic. Huge. Let's see if I can turn that down. Well, that is probably like 8%. I'm gonna guess that is, see, that's about, if that's 1%, so that would be 2, 4, 6, 8, a little over 8% of a second harmonic. However, you know, this is just noise. There is really no other distortion peaks. Now the thing is, second harmonic doesn't really hurt the sound that much. In fact, you probably don't notice it. Perhaps it's what people allude to, the warm sound of tubes. You know, it could be that second harmonic. Now this is not a great circuit by any means, but it does have a very strong second harmonic with no other distortion. Now let's turn the signal back on, and I'll move the scope probe. Okay, now I'll check the signal on the plate, which, being a buffer, it'll be the same. Now the signal on the plate is going to be larger because we were going through those 47 ohm resistors, which kind of act like a divider with the 100 ohm loads, reducing our signal somewhat. But there you go. You see the exact same thing with the distortion. And this is what is on the output. And the chip's doing just what it should, just buffering that signal. Here is the output of the other channel. Yeah, it's pretty much the same thing. 1.78 volts. What's this side? This is a little more. Difference in the tube parameters probably give us a little more amplification on that side. Okay, frequency response test. You can tell it's a sine wave with second harmonics on it. It's not evenly spaced. And it'll drop out a little bit before 20 kilohertz. That's because of the music player. But yeah, no issues with frequency response at all. Well, I sat and listened to a few songs through my Sennheisers here, and the amp does give quite a bit more output than the music player. I have to turn this music player all the way up to get these to perform at a normal listening level, but this amp does give me a lot more output. I don't have to turn it nearly all the way up, so it does give you quite a bit of boost for, you know, playing through headphones. Unfortunately, I cannot give you a sample through headphones for obvious reasons, but what I will try to do is hook this to my computer input and play some music and record it, so you can get an idea, at least through YouTube, what it sounds like. I wanted to try one more thing. The way this circuit's set up, I wanted to see what it would sound like if I plugged in an ordinary wall wart. The one with the transformer, full wave bridge, and filter capacitor type. And see if it would have hum. And absolutely, this thing has a lot of hum. It must have a regulated supply. A clean supply, or it will hum. Being a single element class A bias type stage, any noise on the power supply is going to go right into the buffer here. And yep, there is quite a bit of hum. So what I'll do is connect this to the computer, and I'll have the wall wart plugged in. Then I'll put a clean supply on it and play that through the computer so you can see what it sounds like. Well, there you have it, the little tube-based headphone preamp kit. Thanks again to Matt for sending it in. I'm actually surprised it didn't oscillate not having a supply bypass capacitor, but I've seen stranger things. It is a circuit not without issues, but yeah, I guess you could say it gets the job done. I didn't notice any issues with the sound myself. It does have that heavy second harmonic. Like I say, perhaps that's what people contribute to the warmness of the tube amp sound. But the little buffer chip does pass that right on through, so you get that tube effect. So it's not like it's kind of a decoy where they have a tube in there and it's not really doing much in the circuit. This is actually doing the amplification, and this is the buffering. Well, my battery indicator is going off, so I gotta say adios. Even so, the tube Jeez, I can't talk.